At first glance, an NMR spectrum looks like a chaotic collection of jagged lines. But this graph functions as a precise barcode. Once you understand the pattern, it maps out a molecule's exact carbon-hydrogen skeleton. Decoding that skeleton is a matter of logical deduction. You can solve most organic structures by applying 3 consistent rules of interpretation. These 3 criteria are chemical environments, which determine the number of signals, integration, which measures the area of each peak, and multiplicity, which describes how those peaks split. Applying these observations in a specific sequence provides a consistent way to work backward from a spectrum to a finished molecular structure. Consider 1,1,2 trichloroethane. In this structure, there are 2 distinct proton environments, the CH2 group shown in blue and the CH group shown in red. Because there are 2 distinct environments, the resulting NMR spectrum will show exactly 2 signals. The position of these signals is determined by chemical shift. The 2 chlorine atoms are highly electronegative, so they pull electron density away from the CH proton. This deshields the nucleus, shifting its signal downfield to the left. The CH2 group only has 1 adjacent chlorine, so it remains more shielded. Its signal stays further to the right, or upfield. The value of the chemical shift provides the first piece of evidence regarding which electronegative atoms are located near a specific proton. The second rule is integration. The area under a peak corresponds to the number of protons generating that signal. Here, the CH peak has an area of 1, while the CH2 peak has an area of 2. This diagram from the research materials shows why signals aren't always single spikes. The magnetic spins of protons on adjacent carbons interact with each other, a process called spin-spin splitting. To count these interactions, we only look at neighbors, protons located on the carbon atom directly next to the one we are studying. We use the n+1 rule to predict the split. The CH2 group has exactly 1 neighbor on the adjacent carbon. Since n is 1, 1 + 1 = 2, splitting the signal into a doublet. This figure illustrates the same logic for the other signal. We look at the CH proton and count the neighbors on its adjacent carbon. There are 2 neighboring protons in this case. 2 + 1 = 3, resulting in a triplet with 3 distinct peaks. While integration identifies the number of protons creating the signal, splitting reveals the exact number of protons living on the next carbon over. Look at 1,1 dibromoethane. Based on the rules we just covered, try to predict how many signals it has, their integration, and their splitting. This spectrum shows the result. The CH proton is deshielded by 2 bromines, placing it on the left with an area of 1. The CH3 group is on the right with an area of 3. The CH3 group sees 1 neighbor on the carbon next to it. 1 + 1 = 2, giving this doublet on the right. Looking the other way, the proton H has 3 neighbors. 3 + 1 = 4, creating the quartet on the left. Keeping the count of the absorbing protons separate from the counts of the neighboring protons allows the structure to emerge clearly from the data. The n+1 rule remains consistent even in larger molecules like 2-nitropropane. This diagram highlights a central proton surrounded by 6 identical neighbors. On the actual spectrum, those 6 neighbors plus 1 result in a septet, a single signal split into 7 peaks. To summarize, chemical shift indicates the electronic environment, integration reveals the number of protons represented by the peak, and splitting tells you the number of protons on the adjacent carbon. Following these 3 steps allows you to move from a series of peaks on a page back to the physical arrangement of the molecule.